Alright, so we're going to use Laplace transforms to solve a problem that has a Dirac delta in it. So let's look at y prime plus y equals t times the Dirac delta function of t minus 2. The initial condition is y of 0 equals 0. Remember the Dirac delta function is that unit impulse function. It's like, again, it's the physical interpretation is producing a large magnitude for a short period of time. That's the whole idea behind the Dirac delta function. We know that when we do the Laplace transform of just Dirac of t minus a, that becomes e to the negative sa. In this case, we have t times Dirac delta function of t minus 2. So remember, when we multiply it by a t on the outside, the theorem that we want is if we have t times f of t, we do the negative derivative with respect to s of the Laplace transform of f of s. So when we apply the Laplace transform on the right-hand side, on the left-hand side we have s capital F of s minus little f of 0 plus f of s. On the right-hand side, notice that the Dirac delta function's Laplace transform will be e to the negative 2s. We have to take the derivative of that and do the negative of it. There's that negative out in front as well. So we're going to get equals 2e to the 2s on the right, or negative 2s on the right-hand side. So remember, again, when you've got a power of t here on the outside of a function, you can calculate the Laplace transform by doing whatever the power is, that many derivatives. You have to multiply by the negative 1 to that power. It alternates even, whether it's even or odd, it alternates for that positive and negative. And take the Laplace transform, that many derivatives of the Laplace transform of the thing that the power of t is multiplied by. F of 0 is 0, so that goes away. So we get f of s is going to be 2e to the negative 2s over s plus 1. This one's a pretty straightforward one to do, so I won't bother putting it in GeoGebra, only because I don't want to have to go back and forth between these windows again. This is s plus 1, so its Laplace transform would be e to the negative t. But since I've got a negative 2s here, this is going to be e to the negative t minus 2, and then times the unit step function of t minus 2. So the negative is coming from the fact that this is s minus a minus 1. So that's why we have a negative there. And then the t minus 2 is coming from the fact that we've got this 2 up here, e to the negative 2s. So that's indicating we're going to have a unit step function. And then I have to replace the t with a t minus 2. Again, we could have used GeoGebra. Actually, let's just go ahead and verify it since I don't have to switch back to the window. If we do inverse Laplace transform of, again, that was 2e to the negative 2s, and then divided by s plus 1, we get exactly what we said we're supposed to get. Notice that this is the negative of t minus 2 up there in the exponent. So we get exactly what we said that we had over here. So that gives you an idea of how to do this with the Dirac delta function. The Dirac delta function is an easy one to take the Laplace transform of. In this case, we're using one of those translation theorems that says when you multiply by a power of t, you take a derivative to get its Laplace transform.